I'm here to talk to you about working with large numbers of non-trivial ETL pipelines, or similar to the car story, how I've stuffed it up so you don't have to. So I work for Deckard Technologies, and we're a very new startup, which meant we started from scratch about a year ago. And so this talk is all about our exploration from starting with nothing to working with large numbers of pipelines. So we work with city and county governments in the US, so that's municipal governments. So they take care of property taxes and local laws and all that type of stuff. And we help them find insight in their data. So actionable insight where they can either make or save money, and we give that to them. But we're a modern venture capital-backed startup, so clearly there'd have to be data science in there. So we take all of the crazy amounts of data that these counties have that's in various esoteric forms, we apply data science, and then we get them actionable insights so they can make money. Now, data scientists, as many of you may have come across, are actually quite lazy. They don't want to write a new data model for every single county. So every different county has a different way of describing their data. And even within a county, they all have different ways of describing the same thing. So it's amazing the number of different ways a piece of land can be described. So it can be described the way it is by a GIS engineer, the way it is by a landowner, the way it is by an accountant. So the data scientists want to build off a unified data model. So we build that for them. Now, that's not easy to do because you're doing things like you're pulling stuff out of shapefiles. So you're pulling out of GIS data. We're OCRing PDF forms of things people have applied for data permits for. So first thing we do is we get it into a flat format that we can read in a data lake. Then we apply our unified data model. So our unified data model is a lightly relational model where we have shared keys and similar data types and names. And then at that point, the data science works. So today's talk is just about this component of our data engineering model. So where we go from completely raw data that we pull out of counties, we flatten it so that we can process it in a sort of Spark type environment, and then we create a relational model that our data scientists can work with, but they still have access to the raw data. So the problem space of today's talk is, firstly, what is a non-trivial ETL pipeline? So if you're doing something really simple, so if someone just needs to dump something in an S3 bucket and we need to notice it and throw it into a database, then you really don't need a ETL pipeline. Just use triggers, you're fine. If you need to do multi-steps and at various branching and those steps can fail and you need to find out where they failed, that's where you need an ETL pipeline. And large numbers is, in our case, we need to write a data pipeline and then we need to move on. That customer, we've got that data pipeline, we need to have that data there for our data scientists later on, and we need to stop looking at it. We've only got a very small engineering team and we need to keep moving. So beyond 2 or 3 data pipelines, we needed a way to monitor them. Previously, I've been on big projects where everyone is building into this one data pipeline. People are going to notice when that stops failing, and you've got a different set of monitoring requirements. So our architecture goals is we want to create data pipelines that are easy to debug. So when they do fail, someone who hasn't looked at this code or this system or all these transitions in a long time can work out at what stage it failed and find where it is. We need a system view. So once we're running, I think we're up to something like 117 data pipelines in our small company. And there's about 10 technical people working on that. So we need a way to be able to see which pipelines are running, which are failing, and quickly find out if we can generate a report for an expected customer. So after that, we need monitoring. So it's one thing for a data pipeline to run, but if it's producing 40 or 50 or 60% less data week by week, we need a way to work out if our data pipelines are degrading. Maybe someone has changed the scanner they're using to scan permit applications in, and we're less able to read those documents. So we need we need to notice when things are changing over time and getting worse. And once a pipeline fails, it's all very well that we know it fails, but we need to know who's actually going to fix it. So we quickly ran into alert fatigue where everyone just assumed someone else was dealing with things. So back to our basic flow. We've got our extract layer, so that's where we pull out of the cloud and we get those various data sources in. We've got our transform, so that's when we make our minimum transformations to make it readable in our data lake. So we'll pull things out of a database dump. We'll change an Esri shapefile into a GeoJSON format. So we just do the minimal amount of changes so that we can view it in our data lake. And then finally, we've got our semi-relational loaded model. So whenever possible, show your work. You're going to make mistakes, you're going to make assumptions in your transformations, and they will at some point be wrong. I'm never going to make a claim that what I've created is the right way of doing it. So instead what I do is I just complete transparency. So we allow our data scientists to be able to see, they can go to the raw data and it's listed, they can go to the transformed data and see what particular operations were performed to get us there, and then they can go to the loaded data and see there. So if at any point they have any questions or if their requirements have changed, they can go back and see. So extract. So this is what we look like when we actually run this in AWS. For extract, we either run a Docker container or a Lambda. Originally, a lot of these were Docker containers because even as recently as 12 months ago or 15 months ago when we started, Lambdas were limited at 5 minutes. Many of these counties want to give us a dump of all their data over all time every time we talk to them. So once a month we get, here are our 15 years worth of data, you find the difference. And that takes more than 5 minutes. So where possible, we run Lambda. Where not possible, we run Docker. Then we do our transform step. Once again, this is another Lambda, or if we have to, if it's a Docker, we'll use Docker if we've got to pull in a whole heap of esoteric libraries. Like we've got a lot of GIS libraries we need to load. We need to create a very custom environment for that to do that. So if we have to do that, that's what we do. So our extract stage, we dump completely raw data into S3. So this is exactly as we saw it. So whatever we saw on that day, we dump there, because that's what we'll never be able to get back. Even if the fact that they give us an entire dump the next month, well, we don't know what it looked like at that time if we don't have that original. So we keep everything in S3 in an extract location. Then once we do our transform, we once again put it into S3 into a structured area, into an area we call structured. We then load that into our data catalog using either the AWS Glue crawler or a Lambda where we manually load partitions. What this means is it's now available via Glue, which makes it available via Amazon Athena. Now, Amazon Athena is a Presto implementation, and that allows us to run SQL on top of S3. So we now have SQL access to this data that we've made minimal changes to, so it's available to our data scientists. And finally, our load step. This is where we run AWS Glue. AWS Glue gives us a Spark cluster on demand, so we can just simply write a PySpark script that does our joining and merging and aligning and a lot of address normalization and that type of stuff that makes sense on a Spark cluster, and we can do it on demand. And then we stick that in Parquet, which is a columnar data format, which means it's quick to look up based on groups of columns. And then we partition it by things like zip code so that we can look at chunks of it. So now the data is quick to access in manageable sizes, and it's on S3. And then once again, we stick it in Amazon Athena. So as you can see, at all stages, all of the data is accessible through each transition, and we have a record of what we've done to the data. So one of our other mistakes, we came from an in-house cloud environment, so we stuck all of our S3 stuff in the one bucket with different groups. That was a mistake because things like our extract is the only thing we really need to back up. Everything else can be regenerated. So we've learnt from that lesson now and we've transitioned away from it, but it's an easy trap to fall into. Okay, so we've determined that we want to have we want to have data pipelines, and now we've got to choose which. I've broken these up. There are way more data pipeline more pipelining options than this, but these are some of the most famous ones. And I've broken them into categories. There's the AWS specific ones, so AWS's offering, and the non-AWS offerings. There's the data specific. So the data specific ones normally have database type transitions built into them. We wanted to do a lot more than that. So we want to be able to trigger things to OCR groups of documents and all sorts of things that are outside that frame. So we determined that we wanted a more flexible pipelining tool. We did go with AWS step functions in the end because it has pre-written things for the stuff we needed to do, and manpower is our greatest limitation with an early stage startup, so we just had to go. In the past, I've used Apache Airflow, and it's great, but a lot of its implementation is all about managing your resources and not overloading things and sharing, and we didn't need any of that. So we went with step functions. So what is a step function? I know this slide looks complicated, but it's just a very brief summary. So on the right-hand side, it's a flow diagram. So it allows you to determine a group of steps and how you flow between them. These steps can be a collection of tasks, things like Lambda op functions. You can run AWS batch jobs. Now, AWS batch is how we run our Docker containers. You can manage Glue jobs, as we talked about before. And then finally, there's other states. There are other tasks within that that just process the output of previous tasks and format them for you. On top of that, you can have wait loops. So in our case, we trigger an Athena rebuild. It takes 30 minutes. We don't need our job sitting there waiting for that. So we can put polling in using these wait functions. And then you can do choices and branches and run in parallel and wait and rejoin. And mark success. or fail. And so this is an example of one of our step functions that's run. In this case, extract and transform are being done in the one batch stop. And as you can see, we start the batch job, we run, it completes, we run the Athena rebuild to add the petitions, we then wait, polling to see if it's finished, we check if it's finished, have a look at the result, it's not finished, wait again, check, and it's done. After that, we trigger our glue job because we were successful, we mark that as successful, and then we report the results. And so that's the flow of That's the flow of a step function. So as you can see, we can see what is currently operating at every point in time. Now, each of these tasks takes input from so a step function is made out of a declaration of JSON that defines all the various steps we're going to do and how to do them, and a JSON input that is the input into that function. So each task is able to pull pieces out of that step function input, pull out of its parameters, out of the input path, give those parameters to an AWS resource, such as Lambda or Batch or Glue, take its result and append it to the overall running state input. What this means is that we can write very reusable step functions. So on the left-hand side, I've got a task definition. So this is just one piece of our step function that will run a batch job, and it will reference a lot of things in the input. So in this case, it'll reference the job name we want to run. It will reference the batch job queue, so that's the queue we want to run. We run a lot of our stuff on spot instances. The job definition, so this is the Docker image that it has to run, and then any of the input we give it. So in our case, we give it a big logging blob, which I'm about to talk to. But as you can see, the actual task definition on the left is incredibly generic, and it's all defined by its input. What this has allowed us to do is we actually only have about 6, I think, core step function definitions that run a Lambda, then a Docker, then a Glue, then a Lambda in its various iterations. And then we reuse those in 117 or 120 plus pipelines by giving them all different input, which describes which batch job to run, which Lambda to run, how many instances to create. And so that was a big saving for us. So we have a core stack which defines our step functions, our IAM roles, things like our batch queues and our glue setup. And all of that is shared and when we actually build an individual pipeline, we really only have to write the actual code for that pipeline. So I've got batch there, but that is just shell code that runs on a Docker container when we need it. We've got a glue crawler which defines how we're going to ingest the data. The glue job, that's simply a Spark script which describes how to process the data running on Glue, and then our table. So we've got our data definition language that describes what we're expecting to get out. So each individual pipeline has the minimal amount of code written for it as possible. So we've got this well-maintained core stack, and then every time someone has to write another pipeline, they haven't got to write any more than they really have to. And we set all of these pipelines off using CloudWatch triggers, which could be based on time and so forth. But what we do is we have these triggers defined in our CloudFormation, and they give it which step function we actually want to run. So that's the one of those shared 6 step functions and the input to that step function. And that's how we kick off a pipeline and how we define how that whole process flows. That calls our Lambda, which is set up to start our step function, and that sets the name of the step function and initializes our logging, which I'm going to talk a bit about soon. And then our step function is run and we get our data. Now, the logging. So this was the first problem, is we're now running these tasks on every known AWS service known to man, and our logs are spread across, all of these different places, but many, many more. So when we actually run a pipeline and it fails and data doesn't come out the other end, how do we know what went wrong, or how do we diagnose what went wrong without having to dig all the way in? My first terrible idea, and I blame this on sleep deprivation from trying to get a minimal viable product out, was, well, we'll just use logging handlers and I'll redirect all the logs wherever I want. So each pipeline can create its own logging group, and we can just keep logging to there. This was a nightmare. You talk to AWS support and none of the logs are where they expect it to. Anywhere you click in the UI and it's supposed to take you to logs, you can't find them. It was a terrible plan. Don't do this. Instead, what we do is we just log in JSON and we tag it with all the relevant things. So for us, our customers are based on cities and counties, so we make sure everything's tagged with what county it's for, what city it's for, what type of data. Is it permit data? Is it parcel data? Is it accounting data? And then we tag it with the execution ID so that we can group the logs for one particular run of a pipeline together versus the logs of the other runs. And we use JSON logging for everything. Almost all our code is Python or PySpark, but occasionally we need shell scripts. We've open sourced a tool, we've modified a tool called Bash Banyan to do better logging with that. So even our Bash scripts are logging in JSON. Then we pipe all of those logs to Datadog. There's a couple of different choices. You could use Elasticsearch and so forth. We chose Datadog just because it was quick to get started. Now that we're logging in JSON and we've got all those different fields, on the left-hand side you can see we can sort by facet. So I can pick a step function execution ID, and I can see all of the logs related to that. So I can see what it did in the first Lambda, what it did in the second Lambda, what it did in its Docker file, what happened when it ran on Spark. And I can group all of those logs together, and I can highlight errors. I can see all the logs related to a single county to see if there's any errors there. So I've now got a way to look at what my function is doing from start to finish. Okay, next, did my step function actually run? Is another question we have. So we need to know it ran, and we need to know that the last time it ran, it was successful. So Datadog provides a thing called Datadog checks. I think the main implementation of these were things like you have hosts running and they give CPU checks. So they say whether their CPU is approaching maximum or they're running out of RAM. But they've got an API that lets you run your own checks. So whenever a pipeline completes, we send an OK if it succeeded, we send an error if it failed. And that seemed great. And that allowed us to generate dashboards so we can now see what's happening with all our pipelines and whether they're success or failing. However, so we implemented that. We had a lot of legacy. Our first pipelines tended to run monthly or weekly. Our newer pipelines were running over and over again during the day, and we thought it was all working great. We went to transition the older pipelines, and that's when we discovered that Datadog checks expire after 24 hours. I can find nowhere that this is documented, but this is what happens. And support will confirm this when you actually ask them, is that after 24 hours, they presume a check isn't valid anymore and they throw it away. So this stops this working for a lot of our other jobs. So instead what we do is we replay those checks. So I've got a Lambda job that keeps replaying checks if I think they're still relevant, which is a bit hacky, but it will do for now. For the rest of our monitoring, but that screws up the ability to monitor how many times a pipeline ran, because now we're just seeing how many times the replay ran. So instead we use Datadog Events. Datadog Events allow us to track what happened with our pipelines over months rather than hours. At the end of our job, we either submit an event type of error if it failed, an event type of success if it produced and ran data, or we produce a type of warning if it ran and it produced no data. Sometimes that's okay, but it's not okay too many times in a row. And then we tag all of these with the same fields as our JSON logs, so we can then still look at them and group them in the same way. And this allows us to produce a different kind of dashboard where we can see how many of our, using monitors of those events, how many of them are succeeding or failing. So the other thing we need to do is monitor the metrics. So this is where we monitor how well our jobs are doing. So we want to be able to do that anywhere in our jobs. We want our Glue jobs to be able to report how well they're doing. We want our batch jobs to be able to report how they're doing. So we set up an SNS queue. So anywhere during the pipeline has an easy way, without understanding how Datadog works, to dump their metrics, reporting how much data they generated. And then we can generate dashboards showing over time how much data we're getting, logging the events, viewing the logs. And I'm getting told to wrap up, so I'm going to keep going quite quickly. Then we needed alerting, and we needed to make sure that someone was actually monitoring those alerts. So we linked them into our ticketing system. So that's our solution. Our step functions, at the end, they run a Lambda that reports the results to Datadog, and we've integrated Datadog with Jira. So rather than just generating an alert that goes to our Slack channel that's way too noisy, it actually creates a ticket and assigns it to someone, and even puts that in our sprint. So it gets talked about in the stand-up meeting, what happened, and we know who's dealing with it. And that's how you create alerts if you're going to do it by the UI. We wrote custom Lambdas, so we can actually define all of this as infrastructure as code. So we can define our Datadog alerting and our Datadog monitoring as part of our CloudFormation scripts. And then CloudFormation calls our custom Lambdas to push them to Datadog. And that's overall of our architecture. So we wanted to create pipelines that were easy to debug. We did that with step functions and JSON logging. We wanted to be able to have a whole system view to see what's happening for accounting, so that we did that with dashboards. We wanted to see if they were degrading over time, so we did that with metrics. And finally, we wanted to make sure if they failed that we knew someone was dealing with it. So we did that with Datadog Alerts and Jira. And so to recap, log everything in JSON. Whenever possible, share your step functions. They get quite complicated, so you don't want to have to keep rewriting those. Use the same tags for everything. You want to be able to use those facets for your events, for your monitors, for your logs. And custom resources for CloudFormation are great. They allow us to tear down and put up everything that we need as we need it. And there's no stray things sitting around. Everything is kept in sync. And never move where your logging goes. It is a nightmare. And that's me.